We present light transport applications with a fast flying dot projector. Light transport is a fundamental concept in computer graphics that captures all the interaction in light from a source to a camera. This paper is about dynamic scenes. Our idea is to use a high-speed camera and a MEMS mirror-modulated source to capture dynamic light transport. The MEMS mirror allows for fast scanning of a single light dot over the scene. One application is to integrate all these dot images together to render a virtual floodlit projection of the scene. Here we show two scenes floodlit with our virtual projector. Each image captured by our system consists of many flying dots obtained by fast MEMS scanning. This allows for fast capture of the light transport matrix at video rates. This full capture of the light transport matrix enables relighting of scenes with global illumination, which is not possible with any previous method. Here we show the input relighting illumination for the glass scene. Here we show the relit scene. Note that the caustics on the background are relit with the correct combination of new colors, while the direct specularity is also colored differently in the relit result. Again, our system captures the light transport at each frame in this video. Capturing the light transport allows post-capture relighting to any desired illumination. Here we change the input illumination to a synthetically generated video of colorful bars. Now we show, side by side, the floodlit, flag, and bar illuminated versions of the scene. Note that all of these, including the floodlit, are digitally rendered results using the light transport captured by our system. Our first contribution is the unique combination of a high-speed camera and MEMS mirror to recover the flying dot. This also required a host of calibration algorithms detailed in the paper, such as overlap compensation using a confusion matrix, allowing the removal of radiometric effects. Our second contribution is a suite of post-processing steps, the most important of which is the denoising algorithm that overcomes the issues of low light in our setup. Here we show the raw data floodlit from the setup compared with the output of our post-processing. Our third contribution deals with the non-uniform sampling of the virtual projector. Traditional light transport processing enjoyed elegant solutions to applications, such as transposing to obtain dual imagery, and diagonalization to recover direct components. In our paper, we detailed how to extract these effects using algorithms that do not require grid-like transport sampling. We now show results of our setup. Beginning with relighting of dynamic scenes, we reiterate that in all of our results, the floodlit scene shown as a reference is also a result of our method. Here we show a V-groove being relit with a moving color checker pattern. Note that when the V-groove closes, there are brightening and color bleeding effects due to global illumination. Now we show a wax candle being relit with a colored flag. Note the change in color of the fingers and the candle at the color boundaries. Here we show water streaming over a hand, showing droplets falling that are illuminated by the projector. The hand and droplets are in focus, but the background is out of the depth of field. We encourage the reviewer to pause and see the relighting in the droplets themselves. Now we show a scene where fog, created with dry ice, is imaged by our system. We render a letter A onto the fog. Note the global effects and the warping of the A created by the scattering effects of the fog. We capture the full light transport at each frame, and so we are able to separate direct and global illuminations from a scene. Here we show the V-groove separation. Note that the global illumination is near zero when the V-groove is flat, but becomes pronounced when the V-groove closes. For glass separation, we implement the epipolar constraint recently proposed for separation. For each dot, we get the epipolar line and use masks to accumulate direct and global light separately. Here we show our separation results for the glass scene. Note that the specularity remains in the direct, while the global shows all the caustics. We are also able to render dual videos of the scene. Unlike previous work, we're able to render dual videos without epipolar constraints. Here we show dual views of the V-groove and water scene. While the resolution of the dual videos matches the low resolution of our projector, note that the shadows of the V-groove and the droplets of water are well matched and swapped as expected in dual imagery.